Hello. So we're about to start and hoping people listen to this. Okay. So it is for me a great pleasure to introduce Drew Fudenberg, who's going to be giving the presidential address for the Chronometric Society. Drew has an AB in applied math from Harvard and a PhD in economics from MIT. He spent a long time of his career at Harvard as a professor and now has the Paul A. Samuelson professorship at MIT. He's a member of the National Academy of Sciences and the American Academy of Arts and Sciences. He's received fellowships from the Guggenheim Foundation and from the Alfred P. Sloan Foundation, has more than 100 published journal articles and 4 important books. His work has been in many, many different parts of game theory, and more recently, he's been working on decision theory and behavioral economics. So without further ado, let me please introduce and give welcome to Drew Fudenberg.
Thank you, Eduardo. Before I start, let me congratulate Juan Dubra and Sergio Firpo on their election as fellows of the Econometric Society. If either of you are here, would you please stand up? Well, let's give them a round of applause anyway. And let's also congratulate LACEA on its 25th anniversary. This has been a very important institution for economics in Latin America, and it's great that it's going so strong, so LACEA. And then last, as you know, putting on a good conference like this is a lot of work, and I'd like to thank some of the people who helped make this possible. I don't have time to thank everyone, but I'd like to thank a few of the key people, namely Marcella Morera and Mariano Tomasi, who are co-chairs of the program committee, Federico Wenchelbaum, who is the chair of the local organizing committee, and his staff, Veronica Pipp and Tamara Saluque. So let's give them a round of applause. Okay, so learning, experimentation, and equilibrium refinements in games. I'm going to start off with a non-technical overview, an introduction. Then I'll talk about some work I did with David Levine on learning in extensive form games. Given that he's here, having his photo is perhaps not as important, but those of you who don't recognize him now, well, this is David sailing off to Capri. It looks like he's having a good time. After that, I'll talk about some new work with a phenomenal graduate student, Kevin He, that exploits the connection between learning in games and bandit problems. And here's Kevin outside his hometown of Vancouver. So, learning in games. Most applications of game theory base their predictions on some form of equilibrium concept. But as you know, rationality and even common knowledge of rationality is neither necessary nor sufficient for Nash equilibrium. It's not necessary. Colonies of bacteria can converge to Nash equilibrium. It'd really be straining the definition of rationality to call that rational. It's not sufficient because in a coordination game with multiple pure Nash equilibria, there's no reason to expect any of a Nash equilibria unless there's some reason, like a shared history, that will let players coordinate on a particular equilibrium. So that's an issue for Y equilibrium. Also, if we look in the lab, the first time people play a new game, play is often far from equilibrium. Despite that, equilibrium gives a good approximation of the long-run outcomes of many lab experiments, not all, and it's very useful in the analyses of field data. So this raises some questions. When and why might we expect to see equilibrium play? When we do, which equilibria are more likely to be observed? So that's a big question, and there's a big literature that addresses this by looking at various sorts of non-equilibrium adjustment processes. I could spend the whole hour and a half just surveying the literature. I'm not going to do that. I'm going to focus on one particular kind of learning process, Bayesian learning, with the following properties. The agents in my model will only observe play in their own matches, not what happens in other matches or their opponent's past play. So personal experience. So this is what happens in a typical anonymous random matching design in most lab experiments. Okay. They face, again with random matching, they face randomly drawn opponents from a large population. For that reason, they don't try and influence play of their current partner in the next match, because they won't be playing the same person the next time they play the game. They'll be matched with someone else. Our agents are going to maximize their expected discounted utility given their beliefs. We call them rational discounters. And they believe that they face a fixed but unknown steady state distribution of opponent strategies, which means technically that they think their observations are exchangeable. The order doesn't matter. I'm going to be a little loose and call this stationarity. Why do we assume that? We'll suggest it's a plausible first hypothesis for people in many situations. You don't know what's going on. You might think today is like yesterday. We aren't dogmatic about this. We don't think people always believe in stationarity. They'll reject it given strong evidence that it's wrong. If you're playing matching pennies, your opponent goes heads, tails, heads, tails, heads, tails. You're not learning that he's randomizing 50-50. You're learning that his next play is heads. If we have the strategies or numbers, and you see 1, 2, 3, 4, 5, 6, you could take the average and make that your guess, but 7 seems a pretty obvious thing. Okay? So we don't insist on stationary always, but in the settings we look at, we think it will make sense. So we're going to look at learning. What agents learn depends on what they see when they play the game. And here there's a key difference between the natural observation structure in a static game and an extensive form game. In a static game, so a one-shot simultaneous move game, agents see the realized actions of their opponents at the end of each round, and the action is the same as the opponent's strategy. With my assumption of exchangeable full support priors, the beliefs are going to be asymptotically empirical, meaning the agent's beliefs about the distribution of play will converge to the empirical distribution as the sample grows. So if agents maximize their expected utility given beliefs and play converges to a limit, that limit must be a Nash equilibrium, in the case I'll be talking about, or more generally, if the agents are Bayesians with a misspecified prior, then the steady state must be what Esponda and Puzo call a Burke-Nash equilibrium. Extensive form games, agents, Burke, because there's a famous paper of Burke about learning with misspecified beliefs, agents observe at most the terminal nodes that are reached in their own plays of the game. What does that mean? That means the agent does not observe how their opponents would have played at unreached information sets. Suppose if I go to your store, you can give me good food or bad. If I don't go to your store, I don't see the food. As a result of this, our agent's beliefs with enough data will be consistent, quote, on the path of play, but possibly incorrect otherwise. And play can converge to what David and I called self-confirming equilibria that are not Nash equilibria. For agents to learn about off-path play and rule out these non-Nash outcomes, they must, quote, experiment with off-path actions. They have to get information about what happens off the path. If agents experiment enough that their beliefs at the, quote, relevant information sets are correct, and there's a formal definition of this that I'll spare you, then play cannot end up at a non-Nash steady state. But this poses the question, how much experimenting do we think people will actually do? And which experiments do we think are more likely? What does this imply for the beliefs and play of the agents at these off-path information sets? And thus for which of a Nash equilibria can emerge? One way we could answer these questions, we could write down rules for how the agents experiment. In period 10, play every action with probably 1/100th or something, all sorts of rules. Any rule I wrote down, someone, or maybe several of you, would ask me why this rule and not that rule, and what would happen if the rules changed. So instead of making assumptions directly on how agents experiment and learn, we're going to derive experimentation from optimization. So that's the theme of the talk today. So talk about Bayesian learning in extensive form games. This is work based, as I said, on work with David for the 90s and 2000s, and then newer work I've done with Kevin, including one paper with Lawrence Imhoff. And there's other papers that are in this general area that I'm citing that we'll not be talking about. So in our model, there's a continuum of agents. There's a steady inflow of new agents who do not know the prevailing distribution of strategies, accompanied by an outflow of equal size. So the population size is constant. And it's the different papers in this talk. David and I assume the agents had a finite lifetime, and the newer work with Kevin assumes instead the agents have a geometric distribution. You'll see why that's convenient in a bit. Agents have no prior knowledge of other agents' payoff functions. They're not, okay, that's something you might want to incorporate in people's beliefs, and Kevin and I have done this in the context of signaling games. Agents believe that the system is in a steady state. They just don't know what steady state it is. So what is a steady state? Well, first I should tell you what's a state. A state of a system is a profile of distributions over the histories the agents have seen. So at any given time, some guys are new, haven't seen anything. Some people have played once. Suppose they played once, they played heads, the opponent plays tails. So I've seen heads, comma, tails. Some people have played twice, and they have two observations. And so our history is just a sequence of terminal nodes that you've seen each time you've played the game. Okay. Agents have priors. Here's their distribution of beliefs. Given their beliefs, the agents face a dynamic programming problem. Okay, I haven't written this down yet. You'll see the notation in a bit. This is an overview stage. But the important thing to note is that dynamic programming problems with expected utility maximizers have deterministic solutions. At any history, given anything you've seen in the past, it's without loss of generality to say, or it's not, you might be indifferent, but you're always willing to play a pure rule after any history. That's not to say that people play the same strategy all the time, because your strategy depends on your history. So two agents might have the same rule, and if David's matched with Jean, I'm matched with Eduardo, we see different play, next period we'll play differently. Because there's a continuum of agents, the random matching part of the model is deterministic. So the deterministic rules of the agents generate a deterministic map from the states today, how many people have seen nothing, have seen one heads, have seen this and that, to states tomorrow. How does that happen? Well, given the state and the rule, we know what each agent is doing. Then we match them up. We combine the pairs of strategies. We see what happens. We update everyone's history. Some agents age out and have to leave. New agents come in, and that's how the system updates. A steady state is a fixed point of a map. Okay, and this is a learning system. You might think there shouldn't be steady states because people are learning more and more. How can you get to a steady state? Because the people who leave the system take information with them. So the basic information theory, if you want a steady state, information in has to equal information out. Okay? What do these steady states look like? If the agents are very short-lived, they mostly reflect their prior. If people play only one period, they have a prior, they don't care about the future, play a best response to the prior, and leave. That's sort of a boring steady state. We're going to focus on steady states where agents live a long time. So at least conceivably, their data might swamp their priors. If they're myopic and don't experiment very much, they can maintain mistaken beliefs about how opponents would respond to deviations. And so even if they play many times, play can remain at self-confirming equilibria that are not Nash. And moreover, different agents in the same role might see different outcomes because they're matched with different people, end up playing different things. They could permanently have different beliefs and play different actions. And it turns out if you go look at lab data on play of extensive games in the lab, it's really important not to assume every agent had the same belief. That's something David and I explored in a QJE paper. Okay. We're going to focus now on the patiently stable steady states. Why? Well, the impatient, myopic agents don't experiment. Agents are patient. They have some reason to experiment because they value information. And David and I showed that these patiently stable steady states must correspond to Nash equilibrium. If it's a steady state, it must be Nash. The converse is false in general. Nash equilibrium is not in general sufficient for patient stability. So the point of today's talk is we can develop stronger necessary conditions for steady states with the more careful analysis of how players learn and how they play at information sets that are rarely reached. I'm going to do this first, and depending on time, maybe only, in the context of signaling games. So remind you what a signaling game is. I'll be using the notation. There's an informed sender, call it player 1, observes a type theta from a set capital theta, and chooses a signal S from a set S. There's an exogenous distribution lambda on types. The set of types is finite, and I should have said the set of signals is finite. Everything here is going to be finite. The receiver, player 2, observes the signal, but not the sender's type, and chooses an action, little a. So it's notation for behavior strategies, pi1 and pi2, utility functions u1 and u2, and to lighten the slides, I'm going to assume agents know this distribution lambda, although once you see the model, you'll understand why that doesn't matter. We could have them learn it as well. The key thing about signaling games, Bayes' rule does not pin down the receiver belief about the sender type at off-path signals, at signals that the equilibrium says never should have happened. For that reason, these signaling games typically have many perfect Bayesian equilibrium, supported by different off-path beliefs. And that's created a substantial interest in equilibrium refinements. Cho and Krebs defined a condition called the intuitive criterion to rule out some Nash equilibrium, and they motivated this with arguments about how players would reason about the equilibrium meaning of signals that the equilibrium says should never happen. So that's their approach. That sort of gives me a headache thinking about it. It always did. But let me remind you of one of their examples. This is the beer quiche game. Nature moves first and tells the sender her type. She's either strong or weak. The sender then chooses what to have for breakfast, either quiche or beer. The receiver sees the breakfast, but not the type, decides fight or not fight. Both types of sender would rather not be fought. They gain 2 from not being fought. But the strong type happens to prefer beer, and the weak type happens to prefer quiche. The receiver wants to fight the weak type and not the strong type. So here in the orange or reddish lines is marked a pure strategy Nash equilibrium. Both types of sender have quiche. The receiver does not fight. That is an optimal play because given both types have quiche, the posterior after quiche equals the prior is 0.9. The receiver only wants to fight if the probability of the weak type is at least a half. Okay? So that explains the right half of the diagram. The left half, we say that if the sender has beer, the receiver fights. The sender does not like being fought, so it's happy having quiche, both types. Why does the receiver fight? Because it has beliefs that if it sees beer, it's probably at least a half that the type is weak. And Cho-Krebs argue that this equilibrium is implausible. It's also ruled out by strategic stability. Cho-Krebs appealed to these unset messages to motivate the refinement. Kohlberg-Mertens were motivated by axioms of invariance and iterated dominance. But neither approach is linked to an explanation of when and why equilibrium occurs. And our preferred alternative is to, instead of assuming refinements, we're going to derive refinements from models of learning. In our model, these off-path signals, like having beer, is not counterfactual. They are sometimes played as experiments by young players to gain information. And that lets us derive belief restrictions instead of assuming them. So an outline, here's the key to the argument. Some types of sender have relatively more to gain from experimenting with a given signal. So they send that signal more. So in this example, the strong types have more to gain from sending beer. That generates restrictions on what the receivers see. Therefore, on what they believe when they see the signal, and therefore on how they respond. So let me sketch the model. So as I said before, if agents are rational Bayesians, they have geometrically distributed lifetimes. Each period they continue with probability gamma, which is strictly less than 1. Each sender learns their type when born, which is fixed for life. It's a constant inflow of new senders and receivers that keeps the population size constant, also keeps the type distribution constant. At the end of each period, agents receive a terminal node, the outcome of their match, which in a signaling game is the type and signal of the sender and the action of the receiver. Importantly, though, the senders don't get to see what the receiver would have done if they sent a different signal. So let me talk a bit more about these priors. So first, what space are they defined on? Agents only care about the aggregate distribution of opponents' play, because there's going to be random matching in the model. They don't distinguish between a world where every one of their opponents is mixing 50-50 heads, tails, and half of them always play heads and half always play tails, because either way, the guy you meet tomorrow, 50-50 heads and tails. In addition to that, the agent's beliefs are exchangeable. They think the data is exchangeable. They don't care about the order of the observations, just the empirical distribution. Moreover, we assume the beliefs are regular, which is a technical condition. If they have to have continuous densities. If these densities were strictly positive everywhere, we're done. We're going to try and be a little more general, because we'd like to nest the class of Dirichlet priors, which are widely used in Bayesian statistics and are convenient. Dirichlet priors go to 0 on the boundaries. So we're going to let them go to 0 on the boundaries, but we're going to require they don't go to 0 too fast. And there's exactly one point in the talk where this will matter, and I'll show you where it is. So under these assumptions, beliefs are asymptotically empirical. They converge to the empirical distribution as the sample grows. We're also going to assume that beliefs are independent. In particular, that the response to a signal S does not change the sender's beliefs about how the receiver would have responded to S prime. So if I have beer, I see what happens when I have beer. I get no information about what would have happened if I had quiche. So that's not without loss of generality. It's a substantive restriction. We think of it as a leading special case. More or less plausible in different applications. Why do we make it? This is what's going to give us access to the Giddons index. Okay? The objective function of the agents is to maximize an expected discounted sum of per period profit. The effective discount factor is now gamma, which is your probability continuing, times delta, which is pure rate of time preference. They enter the utility function the same, but they're not the same, right? Because as gamma goes to 1 for fixed delta, most senders live a long time and have lots of data. If we keep gamma fixed and send delta to 1, people don't get lots of data, okay? As gamma goes to 1, most senders live a long time, and we can show, it takes a little work, but not huge amount, but the steady states must be self-confirming equilibria. Patiently stable states are the limits as first gamma goes to 1, so the agents get lots of data, and then the discount factor goes to 1, so they're very patient. So we use this order of limits to make the proof go. We don't have a counterexample about what would go wrong if we reversed it. We just don't know how to do it otherwise. Okay, so that's the setup. I can start telling you results. Okay. I'm going to say that type theta prime is more compatible with signal S prime than type theta double prime if whenever S prime is a weak best response for theta double prime to a receiver strategy, that is when U1, oh, it's a typo. No, it's not. This is fine. Whenever it's so the top line says that S is a weak best response for theta double prime. It's willing to play S. S is at least as good as any other signal for theta double prime. So if that weak inequality holds on the top line, then strict inequality holds on the bottom line. It's a strict best response for the more compatible type. And I've written this using utility functions. You might worry that somehow it's cardinal. No, this is invariant to affine rescaling of utility functions. Why is this of interest? If theta prime is more compatible with the signal than theta double prime, then in any perfect Bayesian equilibrium pi star, theta prime has to play S prime at least as often. Why is that? Well, if theta double prime doesn't play it, if the right-hand side of that inequality is 0, this is vacuously true. If it's not 0, then theta double prime is willing to play S prime. And we said if theta double prime is willing to play S prime, then theta prime strictly wants to. So the left-hand side has to be 1. Okay? So then in this equilibrium, we know that theta prime gives S prime at least as much probability as theta double prime does. So when the receiver sees S prime, she can't update her belief the wrong way. Her belief P, so the posterior odds ratio of theta double prime or theta prime, can't be any more than the prior, because theta double prime isn't doing this thing as much as theta prime. If that's just a consequence of Bayesian equilibrium, we're going to show the same restriction holds at off-path signals. The first step is to characterize individual sender learning and then talk about the aggregate. Here's the first step of the first step. If types theta prime have the same beliefs about receiver strategies, and theta prime is more compatible with the signal than theta double prime, then if theta double prime plays a signal, theta prime does also. So why same beliefs? This is a step. We will relax this. And this is where we use the Giddons index applied to each type's learning problem. So this is something that I had thought was widely known. As I've been giving this talk, I've discovered it's, this sort of age or professional age helps predict probability of knowing this concept, so I'm going to review it a bit. So the Giddons index of a signal S under discount factor beta is the highest expected discounted reward per period under any stopping time tau. Okay. Stopping time, you have to use the signal or the arm once, and then you see what happens. You can continue or stop. Depending on what you've seen, you can keep on going as long as you want or stop. The numerator of this expression is the discounted expected payoff. The denominator is the expected discounted number of times you've pulled the arm. So it's a measure of expected discounted payoff per period. Okay? So that's just a definition of the Giddons index. The index of an arm with a known payoff distribution is the expected value of the arm. You're going to get that payoff every day, no matter what. It's always at least that large, and typically larger. It's larger because of the option value. If you're uncertain of the payoff of the arm, you can see what happens. If you get it looks like it's a good thing, you keep on, a bad thing, stop. So you can get it, it's always at least expected value, could be more. And the Giddons index theorem is that suppose we have a multi-arm bandit. So that's a problem. There's a number of different independent arms, or in our case, signals. What's the optimal rule in this multi-dimensional problem? Compute the index for each arm in isolation as if it were the only arm, and then play in each period the arm with the highest index. So that reduces a multi-dimensional optimization problem to a one-dimensional optimization problem. The optimal rule will eventually use whatever arm is myopically optimal, because the amount the agent expects to learn goes to 0 as he gets more data. So the option value shrinks. Okay? It's possible that the optimal policy locks onto the wrong arm, that will end up under full information, ex post you're making a mistake. The probability of this goes to 0 as the discount factor goes to 1. Intuitively, the more patient you are, the more you experiment, the less likely it is you lock onto the wrong arm. So we want to relate this index, which is a dynamic concept of the stopping rule, to type compatibility, which is static. We'll note that each stopping time for a signal induces a probability distribution over what we call discounted receiver actions observed before stopping. And those expected discounted actions, or distribution of actions, look like they live in the same space as receiver strategies, so we can apply compatibility to them. That's probably a bit mysterious. Here's an example. Suppose the agent believes there's probably half that all the receivers play A1 after S, and probably a half they always play A2. Suppose you're really hoping for A1, and the first time you see A2, you're out. Okay? And okay, so you're going to pull the arm once. If you see A2, you're out. What's the expected discounted probability of A2 under the stopping rule? Well, for sure, well, with probably a half, the guy's playing A2. So it's 0.5, you'll see it in the first period. If you see it in the first period, you never see it again, because you stop. If you don't see it in the first period, you keep on pulling the arm and you never pull it again. Okay? So half the time you pull the arm once and of one A2, half the time you pull it forever and of only A1s. And so the expected discounted probability of A2 is 0.5 over 1 plus this discounted sum of the future periods, which is 1 minus beta over 2 minus beta. So the corresponding receiver strategy is 1 over 2 minus beta and 1 minus beta over 2 minus beta. So note that if beta is near 0, this is like 50-50, because you only care about the first period. It's 50-50 either way. As beta goes to 1, this becomes like 1-0, because you might see A2 once, but you really don't care about one period, and the effect goes away. Okay, so this is an example of this expected discounted distribution of actions induced by a stopping rule. And we show that for each type and each signal, the expression that defines the Giddon index is exactly the payoff against the expected discounted action induced by that stopping rule. Okay? Well, once we have that, the rest is simple. Type theta prime could always use the stopping rule of this other guy, theta double prime. So if theta prime is more compatible with the signal than theta double prime, and the two types have the same beliefs, and S prime has the highest Giddens index for theta double prime, it has to have the highest Giddens index for theta prime, which means that if theta double prime plays it, theta prime does too. So we've just proved this claim. If they have the same beliefs, anytime the less compatible guy plays the strategy, the more compatible guy does. Okay, but that's just one guy with same beliefs. Now I want to find a concept called the aggregate sender response to a receiver strategy. So hold fixed a receiver strategy pi 2 and look at the long-run distribution of strategies used by the senders, given their rules. Okay, the first theorem compared the behavior of two types with the same beliefs. But in the learning model, different types can play different actions, see different things, have different beliefs. So we can't appeal directly to this theorem, but we can use that theorem in a coupling argument to show that the aggregate sender response is co-monotonic with compatibility order. Meaning what? That if theta prime is more compatible with the signal than theta double prime, then for any receiver strategy pi 2, the aggregate sender response, aggregating over all the senders, has theta prime senders play the S prime at least as much as theta double prime. Okay? So that's the key thing we need for our main results. The more compatible guys in aggregate play it more often. And I've just derived it for you, assuming maximization and expected utility. We expect this to hold more generally. You think, well, what if people aren't exactly rational, don't exactly maximize? We still think this property holds. And we've gone to M-Turk and run bandit experiments and seen, yes, people do use more compatible actions more often in bandit problems. So that's the senders. How about the receivers? The senders prior... okay. Should say the receivers prior over sender strategy is arbitrary. So posteriors after signals that are rarely sent might not reflect compatibility. But we show that receiver aggregate play does reflect this order for signals that are sent sufficiently often by the more compatible type, even if the fraction of a time they're sent goes to 0. Okay, and it's this one step in the argument that uses this paper about updating after rare events that we wrote with Lawrence Imhoff. And that's where we use this assumption that the priors can't go to 0 on the boundaries too fast. Not all signals need to be sent sufficiently often by every type. For example, if a given signal is strictly dominated for a type, it will never send it. There's nothing to learn. But as delta goes to 1, each type, theta, does send signal S often if there's some possible, another typo, I apologize. Yeah. Receiver response would be better than the type steady state payoff. That is, if the utility max over all receiver actions A, if U1 of theta S and A, is better than what type theta is getting in the equilibrium pi star. So if something could possibly beat equilibrium, you'll try it. Let capital P of, hopefully you can read this, of theta triangle, theta prime triangle, theta double prime be the set of distributions where the odds ratio for theta double prime to theta prime is at most a prior. This should remind you of the compatibility condition. We'll say that a strategy profile pi star satisfies the compatibility criterion if the receiver response to each signal S is a best response to beliefs in each of these P of theta prime triangle theta double prime whenever two things are true. The first one is theta prime is more compatible with the signal than theta double prime, so it sends it more. And the second one is that theta prime has some reason to send it. See, the first condition is consistent with neither guy either wanting to send it at all. They could both send it 0 times. The second condition says that theta prime does send it pretty often. And the theorem of the paper is that if the profile is patiently stable, it has to satisfy this compatibility condition. In the both quiche equilibrium of the beer-quiche game, the strong type has reason to experiment with beer, but the weak type doesn't. So if we tried to have a steady state where people had quiche, only the strong types would experiment. And so this pooling on quiche is ruled out by the compatibility criterion. Because if the belief, the posterior after you see beer is at least a prior, the receiver would not fight. That conclusion depends on the prior, and if we change the prior, it would fail. But a related result only holds for pure strategy equilibrium, lets us rule out pooling on quiche for any prior. Okay, so that's end of first paper, and that was 35 minutes, good. Briefly on the second paper, you might be wondering, how does your new refinement compare to stuff in the literature? Cho-Krebs, divinity. Well, most of the signaling game refinements are based on senders being certain that receivers don't play dominated strategies. That conflicts with our non-doctrinaire prior assumption, strictly positive weight on all opponent strategies. So we look at what happens if instead we let the senders assign probability 0 to strictly dominated strategies of receivers. We still want non-doctrinaire priors on everything else, but you can put probability 0 on opponent strategies that are strictly dominated. And that generates a solution concept we call rational compatibility. The rationality is players know their opponent's payoff functions. Rational compatibility implies the Cho-Krebs intuitive criterion. And we show that it's similar to divine equilibrium. It's not quite the same. And I'll spare you the details. Another thing the second paper does is develop direct sufficient conditions for patient stability. What do I mean by that? Well, steady states always exist, so patiently stable steady states exist. So if you show me a game with 2 Nash equilibria, and one of them is not patiently stable, the other one is. So that's an indirect proof that works in, say, the beer-quiche game, but we also have a direct proof that a sufficient condition on the equilibrium. Okay. Let me circle back to some stuff with David to put this in perspective. He and I have this AER paper on learning in simple games. Simple games are games of perfect information where each player only moves once on any path of play. So in these games, sequential equilibrium is really strong. Generically, there's a unique sequential equilibrium in a game of perfect information. But those restrictions are not implied by rational learning. Instead, every subgame confirmed equilibrium is patiently stable. So why is that? Why don't we get backwards induction? Because if an information set is rarely reached, the player moving there doesn't expect to get to play again for a very long time. And we can cook things up in a way that even as the player becomes arbitrarily patient, it chooses not to experiment that an off-path information set gets no information about what happens afterwards, so we don't get backwards induction. Every sequential equilibrium is subgame confirmed. So in simple games, patient learning never rules out a sequential equilibrium, and it typically allows others. In signaling games, the reverse is true. Patient learning makes stronger predictions than sequential equilibrium. Okay? What's going on? Well, in signaling games, the relative probabilities of experiments matters because it influences beliefs at these non-singleton off-path information sets, beliefs about the sender's type. In a game where every information is a singleton, there are no beliefs at information, so this whole channel is gone in simple games. On the other hand, receivers don't need to experiment in signaling games, which is why it didn't matter if we assumed that the distribution of types was known or not. No player moves after them. They see the sender's type at the end of each round, so we don't have to worry about do people off-path experiment in signaling games. And for the same reason, subgame confirmed is the same as sequential equilibrium in simple games that only have length 2. Okay, good. Paper 3, player-compatible equilibrium. This is more on the theme of linking up to refinements. Much of the refinement literature, so not Cho-Krebs, but proper equilibrium and Kohlberg-Mertens, etc., use the device of, quote, trembles, small mistakes, to define the concept. One way of thinking about what we're doing here with optimal learning is we're identifying trembles with experiments and then deducing which trembles are most likely. So player-compatible equilibrium generalizes that outside of signaling games. Like proper equilibrium, we select equilibria that are robust to sequences of trembles. Okay, and the wording here isn't quite right. Apologize on that too. Let me burn 1 minute and tell you the story. I revised the slides for this talk, fixing some things. My hard drive died this morning before I sent the file off. So I spent much of a day in the business center re-revising my slides. Luckily I could do it. Some things that were fixed before I forgot to fix. So anyhow, so this player-compatible equilibrium reduces to the compatibility criterion I showed you in signaling games. It's more general. It only has bite if we can somehow say this player is more compatible with an action than that player is. So here's an example, a game of link formation. There's 2 sets of players, north and south. There's like maybe 2 north and 2 south, or 4 north and 4 south. Every player simultaneously chooses whether or not to be active. Inactive players get 0. Active players form links with all the active players on the other side. So if I'm a north and I active, every south who picked active I linked with. You then pay a cost per active link that depends on you and get a benefit depending on who you link to. So some people are better to link with than others. And we write down the paths in such a way that there are 2 pure Nash equilibria. Everyone active and no one active. And standard refinements get nowhere in distinguishing between these equilibria. There's no standard refinement, including pairwise stability, that can make different predictions in these 2 games. Make different predictions depending on payoffs, okay? Slowing down. I'm going to compare 2 versions of these games, okay? So it's always the case that low-cost players are more compatible with being active. If no one's active, you might experiment with active, see what happens. If it's cheaper, you should do it. If the low-cost guys also provide the highest benefit, then we say the low-cost guys tremble more onto active. Everyone else wants to be active, so that's the only PCE. If the low-cost players give low benefit, then both pure equilibria are PCE. So we don't get the ideal case of point prediction here, different point prediction there. We get different predictions. But if we look at learning dynamics starting from uniform prior, we think all inactive would be more likely. Okay. So now I can circle back and say we have this difference in predictions. Standard refinements, there's no standard refinement that makes different predictions in these 2 cases. Okay. The paper has a few other examples, existence, comparison to concepts. Let me tell you about the last paper I will impose on you. Predicting lab outcomes using learning theory. So hopefully this will have multiple experiments. We only have one design approved so far, which is the link formation game that I showed you. When have groups of 4 play the game 20 times with anonymous random matching. So in either the co-monotonic treatment or the anti-monotonic treatment. Is it the high-cost guys or the low-cost guys who are good to match with? And what we did, we pre-registered 4 predictions about the experiment before we went to the lab on a website called aspredicted.org. So, and I was worried about time, so I didn't list all the predictions. I'm just showing you one of them here, which is that we'll see more than half the links active in the treatment where this is unique PCE, and less than half the links active when it's more compatible players are worse to match with. So we're still running sessions. We don't have all the data. It looks pretty good. It's not, I said there's 4 predictions, so far 3 look really good, and one of them is kind of iffy, so yeah. So a few of you may know that about 2010, I wrote an essay for the NSF about futures of game theory that advocated predictive game theory as a thing we should do to try and make predictions. So at the time, that was mostly sort of do as I say, not as I do. So I feel like I'm finally delivering on the polemics of that paper. Okay. So conclusions. The outcome of a game doesn't reveal the opponent's complete extensive form strategies, so incorrect beliefs and self-confirming equilibria can persist for a long time unless players experiment with off-path actions. When players are patient, they will experiment with off-path actions, at least some off-path actions, many times. And that leads not only to Nash equilibrium, but to refinements of Nash equilibrium based on which experiments are done more often. In signaling games, the steady states with patient learners have to satisfy the compatibility criterion. Rational learning models can be used to generate predictions in other games too. Many of these predictions extend to variants of the model with less rationality and are other sources of information. So in our model, it was purely personal information. People only learn from own experience. You might think, you might learn some things from your friends, parents, or newspapers, and to a certain extent, the results extend. A cheap extension is all the results I showed you go through as stated. If some fraction of players get to see what's going on in their world for free, as long as there's a fraction of people who are uninformed, then it'll be their experiments that drive the play. Okay. So, but that's maybe a cheap extension. We could look at more interesting extensions of social learning that should be done. And we should also investigate how well our predictions fit the outcomes of lab experiments. And thank you so much for staying to the end of the day. Oh, great, wonderful. It's true.
We have a couple of minutes, so...
Wonderful. I'd be delighted to take questions. Please. But maybe he needs it out there. I can go back. I came over here to hear him.
Zach, then you can stay here.
Yeah, I should stay there.
You did a great job. Now, the question again.
Other questions? Did I take care of your question correctly? Okay. Try again?
I'm not sure if I understood, but I just wanted to understand if, okay, so if agents are not infinitely patient,
Yeah.
can you make...
No, so the reason it's hard so for a general discount factor is self-confirming. You might think as people get more and more patient, the set shrinks. How much it shrinks depends on how confident agents were of their prior, how much data it will take them to offset their prior. If you gave me a uniform bound on the density of the prior, then I could say for given deltas, I could do something. But we want the results to hold for any regular prior, which is why then you, in principle, need arbitrarily much data, and so we need people to be very patient to do that much experiments. So that's what's going on there. You know, you could, you know, if you did put a bound on the density, then I think numerically there'd be some hope of having results. But we have no such results.
Okay. It's been a long day and a wonderful talk. Thank you very much, and it's time to tango. Thanks a lot for a wonderful talk.